Okay, hello. We are starting, and today we have, as usual before the event, we have a workshop. And my name is Oleksiy Semenyaka. I'm working for RIPE NCC. I'm a technical advisor in the RIPE NCC, and I will discuss today the new technology, quite promising, and for some large network already quite important, called segment routing for IPv6, SRv6. And we will start from the general overview. Why we need something like this anyway? Actually, it was clear from the very beginning that in our networks we have different objects, different applications with different requirements, which produce different types of traffic. And our network consists of different channels, different types of channels. So we have to simplify this to make it work. But as I said from the very beginning, there was an idea that probably we can add something to our ideology, to our TCP/IP ideology, which can make it better. And usual approach was to find a way to predefine routing, to have some kind of predefined routing in our network, to work in parallel with our standard distributed routing we used to have. And what it can provide us? It can provide us with traffic engineering. And this traffic engineering, it can be really simple if we managed to do the efficient predefined routing. And if we have the traffic engineering, we can get better capacity planning, because the load of our links now is explicitly controlled. We can use a rich matrix, because for distributed routing, you understand that we have to reduce all things we have, all aspects we have in the network into one value to make it comparable across the network. With explicit traffic engineering, we can do much more cumbersome routing decisions. And we can get rid of these small fluctuations which we have when we have recalculation of routes, when we have desynchronization of our nodes for short periods of time, but still we see this jitter in our network. We see maybe subtle but still losses in our network. So we want to cope with this. And of course, we can provide with more more efficient partition, and we can structure our network not with some coarse approach, but do it granularly, and it can give us much more robust and much more reliable fast routing. Once again, we are speaking of dreams. We will see how they can or can't go to reality, but still. And with this approach, probably we could have effortless management and simple diagnostics, because we have explicit paths and it's easy to manage them. So the first attempts started back then, when IPv4 IPv4 was created, and it was source routing options. It was quite naive and simple approach, loose source routing, strict source routing, you remember that. And approximately at the end of the last century, it became clear that it doesn't work. It creates much more issues and problems than it solves. And the main drawback is that we have security issues, severe security issues related to that. So at early years of this century, it was completely deprecated and removed from the operating systems. The next approach, called routing header type 0, appeared in IPv6. Once again, from the very beginning, if you have routing header, it should do something, right? So we try to reproduce the same approach, source routing, but using the structure of the extension header in IPv6. And not surprisingly, it turned out that it has same set of issues. So in 2007, it was completely deprecated and prohibited. Then another approach was to develop the path computational elements approach and corresponding path computational elements protocol with predefined routing. It was invented in 2006, and the idea was to move shortest path first from our different routers to unified controller in somewhere in the center of our network, to reduce the amount of calculations, to reduce the amount of states in our network, and to have all these calculations in one place. So this controller could instruct our routers after that, and everything should work synchronously. This approach never died, but for a long time it has the real modest area where it was used. It was RSVPT and GMPLS, and there, unfortunately, we didn't solve the problem of states. We still had a lot of states in our networks, and so it could be used for some specific needs, but it could not be scaled to the whole network. And another approach is completely revolutionary one, was OpenFlow SDN. You should remember that it was not that long time ago when everybody discussed this OpenFlow, and it was invented in 2008, but most of hype we had in 2012 approximately. And the idea is to physically separate our control plane and our data plane. And if we achieve this goal, we could go away from these, big smart boxes, which are really expensive and which are providing us with all stuff like vendor locks and everything. We can switch to small, stupid, simple white boxes. And approximately in 10 years, it was completely written off. Why? Because this approach, it turned out that it has internal contradictions, internal conflicts. Because with this approach, when everything is decided by some open flow controller, our boxes now need a lot of TCOM. And ASICs are not enough now for them. They need network processors. So instead of this, cheap like dirt, white boxes, now we have some special, really expensive devices, and all of them have to be like this. Also, when we have all decision made somewhere, we have the latency problem. Before, if ASIC has some unknown packet, it can ask CPU. Now it has to ask controller. Nanoseconds versus microseconds. And the complexity of these updates, because anyway this box has to keep the model, the tables, and this of the forwarding rules, and these tables should be multi-level to deal with the real complexity of our real networks, and updates are coming, so we have to keep several versions. The complexity of this solution was overwhelming. So this approach with complete micromanagement is also that. So the next attempt to bite this apple was taken in 2013. It was called segment routing, at the moment without IPv6. It was MPLS based, and it was successful. It was successful enough because authors decided to move away from the micromanagement approach. They didn't try to cover everything. They decided to combine the distributed approach and predefined decision making. And what it needed and what was done is rethinking, redefining the meaning of labels in MPLS. And after that, the next step, the natural step, which we have now, was switching from MPLS to IPv6. Because in IPv6 we have a lot of flexibility, we have a lot of internal structures which can help us to solve the problem. And it's much easier than to work with MPLS. So segment routing in IPv6 adapted core concepts from segment routing MPLS, and that's why later I will start from segment routing MPLS to introduce you concepts, and then we will switch to to IPv6 specifics. And with IPv6 we have simpler deployment because we don't need to deal with the special thing like MPLS. It's the normal IPv6. We can have an easy adaptation, but due to these features, we also have some drawbacks which we will, of course, discuss later. So a short recap, maybe not. Can I skip this slide, or and everybody remembers what MPLS is, or should I spend 1 minute for the recap? Come on. Skip. Okay. So for MPLS, everything is obvious. It's extremely simple thing on the data plane, simple thing in the world, with a really, really complex control plane. So segment routing decided to get rid of this hierarchy of labels and redefined labels at the sequence of some entities. So labels are not local anymore. They are fixed over the network. And they are not overwritten anymore. They are fixed over the network. And each label represents a specific network entity, which called a segment. So label value is the identifier of this segment, or segment ID, or SID. And these segments may be of different kind, and that's completely normal. And now a label stack is the sequence of segments in which in the order the packet should pass. So we are explicitly defining the sequence of these segments. And what are these segments, these entities, because obviously it's not clear yet? The simplest example of them are nodes or links. And for example, if we go for our segments to be nodes, basically we have the structure really similar to what we had in our traditional source routing, like RH0. Really almost the same from the structural point of view. But we can have not only nodes, we can have, for example, our links, as I mentioned. And if we say that the SID sequence is, you see here, A, B, X, what does it mean? It means that you should go to A. I am not telling you how. The local router will decide. Then you should go to B. That the router B will decide. The only question is that you have to be on the node B. And finally, you have to go through the link X to the node C. So here on this part of the network, I am telling you that from B to C, you should go explicitly through the link X. So the idea is simple, but actually it can be generalized, and it was generalized. So any operation we can perform with our IP packet can be a segment. You should go to the tunnel, or welcome to the scrubbing center because we are under the DDoS attack. Anything, it can be described and coded as a segment. And it is defined by the source, but only this general sequence. Not, we don't go for details if we don't want to. From A to B, the router will decide how to forward this packet, as an example. So basically, what does it mean? That means that we can describe the capabilities, the ways we are we want to deal with on each router, and then selecting a next segment means that we are choosing the instruction, or in segment routing we call it function, of the router, what to do with this packet. And thus, the sequence of SIDs is a program. Basically, we have function encoded in SIDs, and that's defined what router is instructed to do. And according to this, it behaves in the way it should. So now we are programming our network. Now we are not dealing with some simple behavior. It's quite a complex way to describe things. We are adding complex behavior of any our network element, and our network becomes programmable. And some examples of functions to give you the idea, like please go directly to the by the shortest path to this node, or go to the specific link, or please go to the IPv4 VPN, or the last one should be IPv6, sorry, or IPv6 VPN. And this is described exactly the same way. And it's up to the entry point of this network how to program our packet. So when we are saying these words, the entry, we have to define entry to what. And that's important part of this segment routing approach, defining the segment routing domain. We are clearly defining the part of our network, or maybe all internal network, as a segment routing domain. And we are using the specific labels there, which are treated the specific way. MPLS knows that this range is devoted for segment routing, and it can be combined on the borders with the traditional MPLS. So that's a simple but important, really important concept, which I will refer to later. And how to form, here the list of sequences of seed, how to signal them over the network. Actually, we can use the pre-configured seeds, like if you are sending packet from here to there, use this seed sequence, this segment routing path. Or we can use IGP with the proper extensions. These extensions are simple, and I will describe them a little bit later. But also, we can go for SDN controller. And now this is not SDN which is controlling everything. It's programming our network. It's not producing, instructions just for fun. That's the reasonable amount of interaction between the controller and the routers. And the routers still have some zone of responsibility where they are deciding. And here you can use same IGPs, or you can use BGP LS link state, or you can use once again PSAP protocol or netconf approach, and you can mix them. So that's the dream. Unfortunately, the dream, how two hosts can be connected through the segment routing network with two data centers on the left and on the right, and some core network in between, and everything is controlled by segment routing. This picture was introduced by Bell Canada in 2016, and then it was taken by Cisco in their description of a segment routing protocol as an example. But once again, that's the dream. It never came to to the reality. So why? What issues do we have here? We still need to have MPLS everywhere, and not only MPLS, it's advanced MPLS. It's MPLS which understands segment routing, and when we come to this, ASICs don't like too many MPLS labels, so we have to deal with small amount of labels. So we have to use some label compression and everything. So the idea was really simple, but in reality, deployment of this means the total change in your networks, too expensive, too time and energy consuming, too risky, and so on. So can we take these ideas and translate to something simpler, to IPv6? Some people, it was, if I remember right, 2015, decided that it's completely a reasonable thing to do. We still have a routing header. Yes, routing header of type 0 is deprecated, but the entity, the routing header, so routing extension header is still there, and it's large. We can put a lot of things there, and it's easy to use because the structure is completely transparent. And with this approach, we always have a backup, which is the basic header. We still can use our IPv6 traditional routing. So it might be much easier, and it turned out that it is. So what we are doing with segment routing version 6, we translate MPLS into IPv6. And now we introduce the routing header type 4, which called segment routing header, SRh. And now our seeds are IPv6 addresses. In the traditional segment routing with MPLS, we had 20 bits. Here we have much more bits. In general, we have 128, but of course, these addresses should be in our address space, so the real amount of bit to operate a little bit less. But still, it's a huge size. And because we have so many bits, we can devote some of them for the so-called locator part. Locator part defines where this element is in the network, and we can to find out where, we can use the traditional approach, our traditional internal gateway protocols. Now, also we have function, so-called function. It's the same idea that we had in the MPLS segment routing, but now it's explicit. We have these bits from here to here is the identifier of our function. It's simple. And we can even add, if we need, some arguments. It's not necessary, but still we can do that. If we have same functions with, with some additional cherry on the top, we can code this cherry with the argument. So the structure is simple. The structure of segment routing header is a little bit more complex, but if we start thinking, it's not difficult. We have the basic information like next header, routing type, which is 4. We can field segments left to describe which segment should be used on this hop. We have the list of these segments, which are, as I said, just normal IP addresses. And we have an optional area with some specific TLV type and level and value tuples. So there we can add some additional information about the whole segment routing header. At the moment, the only TLV we are having described is the signature of all this to prevent intrusion into the segment list area. But in future, maybe we will have some additional functionality. Now, let's summarize which differences we have with segment routing version 6 versus segment routing with MPLS. We are using IP addresses instead of labels. Obviously, I mentioned that. And now we are not popping these addresses. We are not changing anything. We are just moving our pointer, which is this guy. Looks like I don't have here the laser pointer. So this yellow guy on the top right segments left, we are just changing this on this hop, and nothing else is changed. It's simple and cheap. And when we change this pointer, we are copying the next seed into the destination IP. So the list of these segments is an explicit list of IP addresses to pass through, with IP addresses having the specific meaning, like function and everything. So it means that if we have in our networks the usual traditional IPv6 devices, they will deal with this packet completely correct. It will be passed to the proper node. Now we need the support of this technology only in key points where these functions will be used. All other networks can be just standard, usual, traditional IPv6 network without any changes. Once again, only key point should be changed, upgraded to use this technology. And here how it works. At the beginning, we start with the first seed, then this seed is copied to the destination IP. The packet goes through the network and reaches the corresponding node. This node sees that the packet has SRh. Now it performs the function programmed in the seed, right? And then it shifts the pointer and performs the next step. And this way, it goes from node to node through our network in the programmable way. And here, because we have all these functions, all these things inside our network, it's important to remind you that the crucial part of all this thing is planning, including the address planning. Because still, we have longest prefix match in our network we didn't get rid of. So we can optimize our network and make our life tomorrow much easier if we use aggregation of our addresses. And to use aggregation of our addresses, we need to build the whole address plan, which takes into account that now we have a SRv6 address block inside our location. And inside this address block, we have locators prefixes. Inside these locators prefixes, we have functions prefixes. And some functions might need arguments, so we need extra bits for that. And it's completely reasonable to keep to keep the width of all parts the same. So we have to describe first our segment routing structure. We have to understand each part of that. Then we have to unify the width in each part of address plan, and then gather everything and add to the common address plan of our network. Now, the obvious question is who and how is producing this header. The idea is clear. I can form the sequence of header of seeds, and I understand how router SRv6 capable router will deal with these. I need just to turn it on. It's obvious, but how I'm forming this header anyway. So here we have the special name for the guy who is doing this, the node which generates SRh. It's called headend. That's the entry to the SRv6 domain. And it can do it different ways. It can do it a static way with explicit description of the sequence. It can do it dynamically. And it can combine different approaches. So how we do this? Describe it by so-called segment routing policy. And segment routing policy, it's worth to remember that it can produce several path candidates. In the simplest story, we have just one, or we have the best one, and we are using this. But tomorrow, or even today, if it's really necessary, we can use different path candidates because segment routing policy produce us weights for them, and now we can start a complex traffic engineering using different paths over our network to distribute traffic in equal way, for example. So this idea of segment routing policy is an important concept for the technology as well. And the most simple example of this policy is just our traditional, usual, shortest path tree. In this approach, you will have exactly the same results as you have in the traditional routing. So it's a good point to start with before you will start using advantage of the technology. And I'm sorry. How do we insert the header into the packet? Actually, usually we don't. At the beginning of the technology, the people decided to insert it, to add to the existing packet the SRh, and change the behavior of the existing packet. But then this idea was discarded after the huge amount of discussions, and it was really hot discussions with different arguments, but at the end of them, industry decided that no, we don't insert SRh into the transit traffic. Never. It's prohibited. We either forming SRh from the very beginning if our host is segment routing capable, it can produce SRh itself. If it doesn't, we are using encapsulating. So basically, we are switching to the traditional underlayer and overlayer networks. And the underlay works in a traditional way. And all our logic or all our applications, as usual, they live in overlay, right? So at the moment, the first approach, insertion of segment routing header, is not implemented anywhere. It's, as I mentioned, it's allowed for hosts, but it's not used there. Operating systems do not support that. Maybe yet, but at the moment it's like this. And now, if we have this overlaying infrastructure, how we can track our packets? Because usually we are using ping, we are using traceroute. What do we have here? Here inside the flags field, we have so-called O bit, and that's the only bit we are using at the moment to signal the telemetry data. When router sees this O bit, it takes some telemetry data from the packet, sends it to CPU to do something with this, for example, to send a traceroute reply, and packets go the standard way. So it's done by the CPU, not by ASIC. We are not losing the rate here. And that's the Linux example. Linux is supporting segment routing for quite a long time. So to start with the the static segment routing policy, we can use just this command you see on the screen. It's simple. So we can start doing this immediately, and you can spot here the word incap. So theoretically, as I said, Linux can insert SRh, but in reality it doesn't. It uses the encapsulation as well. So that's clear if we are speaking of the static configuration, but of course we want to use dynamics in our network. We want to react to events we have in our network, what we can do. And here the first approach we can use for modest networks, we can start with a simpler architecture without any controller, using just IGPs. How does it work? IGP distributes locators and topological information as usual. The IGP distributes the topological information, it should, but with some additional things. And that's enough to build the topology view on the endpoint with corresponding seeds. But if we want to describe our services, we can also use BGP, BGP-LS, link state BGP, which is not a routing protocol, it's a signaling protocol describing the state of the network. And there we have some additional parts to describe our functions. So you don't need to, to invent anything. If the corresponding modification of BGP-LS is supported by your equipment, you just turn it on, and now you have signaling of functions on your network devices all over the network. And as I said, the head end now can calculate the candidate paths and choose one of them or several of them if we are doing the traffic engineering. What IGP support do we need here? Actually, let's take a look on OSPF as an example. And that's really simple. Now, we are distributing the information of our locators because it's our prefixes in our network, and we need to know where each of them is located. That's the classical OSPF. Nothing changed here. Now, for LSAs describing the node, we are adding sub-TLV, this seed for this node. For our links, for each router, for corresponding LSA, we are adding the sub-TLV describing the seed for this link. And that's it. That's simple. We have all these things inside IGP. We are just adding names to them and nothing more. So now, with this, you can start using dynamic segment routing if you are using OSPF version 3 with segment routing extensions. Really simple, because all the information is distributed over all devices. And by the way, Linux is supporting this with, say, FRR. So it could be extended up to the host. And now, probably you want more flexibility, more power, and you are starting off doing SRv6 controller. And it's important to understand that there is a huge difference between OpenFlow controller and segment routing v6 controller. In segment routing v6, controller does not enable the technology. It makes orchestration and it adds scalability to our calculations, but not more. And how does it work? It collects the information usually using BGP-LS. So you are enabling BGP-LS in your network on some keynodes. Then you are turning on BGP-LS on the controller, and you are connecting controller to your headends using PSAP protocol. So now controller is calculating paths over the network and signaling these pre-calculated paths to headends with path computational elements protocol. And here, this PSAP, that's exactly the place where it's completely suitable. And now it can be, it's using in the whole network, because we are not keeping states anymore, and it's completely scalable. And of course, by providing this path, we are not replacing our underlay routing. We still need this. We're still doing, our IGP, we're still using longest prefix match and everything. So we are not changing too much. We are just adding the scalability with this guy called SRv6 controller. And that's controller now who is responsible for determining the policy. And now the traffic engineering is absolutely flexible. You can do whatever you want. You can choose, you can construct your headends with using different paths depending on your current policies, depending on your current situation, or even you can connect it to the provisioning system. For example, for client X, you need to create a path from A to T, and it will be done automatically without any additional efforts. So it's really up to you how far you can go with this controller and which controller are you using, because it's completely programmable thing. And of course, here we also have fast reroute, because it was important, and nobody in the world would start using the technology without fast reroute, right? So here it's called topology independent loop-free alternate, TILFA. Long abbreviation, but the idea is extremely simple. If you turn this capability on SRv6 capable routers, they start tracking the information about the state of the network, and they are pre-calculating alternative paths to the destination. Now imagine that some router detects an outage. What does it do? It's simple. It starts being a headend. It uses one more layer of segment routing, adding additional encapsulation with the SRh having the path around this outage. And as long as we have this issue, it will pass the traffic around this outage in the most optimal, from its point of view, way. When it's over, it will switch to the normal operations. And because we have all the things like functions in our network, it's easy to signal that I'm starting doing TILFA. So your function is to remove this layer of SRv6 and start doing the SRv6 from inside. That's just additional function inside our network, additional IPv6 address signaling that your behavior should be like this. And it starts working immediately when this PLR, point of local repair, sees the problem. And the really important thing here is the security, because the technology is powerful. It can do a lot of things, and it's really flexible. And with flexibility, usually the security issues come. And the very first question, and I had this question as well myself when I started learning this technology. What is the difference between segment routing and this outdated, deprecated pesky RH0? They are really similar in terms of the routing header structure. And the question is how to, how to deal with this. And the answer is, and it was built in the technology from the very beginning, that we are working in our area, trusted area. And it's important to keep all policy working, because the technology, it's not about, the structure of header or the description of protocol. The technology necessarily includes also our policies, and these policies should be fulfilled. So we are using trust boundary, and we have to control that no SRh comes from outside. Otherwise, we are doomed. And even if we have this trust boundary, it's really wise to check, to validate the source address and other information on the level of internal segment routing version 6 capable nodes. So this node, even if this node gets some packet, it should perform the basic check if this packet can be here. And it also works for the control plane, because if we have our IGP with segment routing add-ons, and these add-ons can be sent from outside, from untrusted domain, then our network can be completely screwed up, right? So that's important to remember. That should not be sub-item. Theoretically, when they describe segment routing, they mention that, we have HMAC signatures in SRh, and we can use them to protect our seed information. And that's a partial truth, because theoretically in the standard we do have that. We have this TLV with the signatures described, but they are not implemented anywhere except with Linux. So inside your network, you are not able to check them, because it's not realistic to set up the transition Linux boxes inside your network and treat this amount of traffic you usually have in the internal network, checking the signature. So it doesn't work. I want to be honest. This part exists only on paper. Another aspect to remember, we have to remember that this routing header, it's large. It's not something small, it's large. So we have to remember of MTU issues we can encounter here. Usually, you have Jumbo frames inside your network inside your internal network, and for internet traffic, it's enough to combine Jumbo MTU and standard MTU sizes for the internet, but still, it's important to remember. Another thing is that ASICs, they are limited in their functions. Same as with the labels, they are not capable to scan too much seeds inside SRh. And the amount of seeds described as maximum seed depth, and the standard defines several of them actually for different scenarios. It can be this number can be different, but it's still not huge. So you have to find out first what MSD for your equipment is, and plan your network accordingly. So it's not unlimited capabilities, it's limited to your ASICs. Of course, modern ASICs doing better than old ones, but even the modern ASICs are not capable to deal with, for example, 100 of seeds. I mean, they are capable, but the rate will be terrible, so you don't want to do that. And remember of this old bit, it should be enabled. Any equipment supporting segment routing version 6 at the moment supports all bit, but sometimes you need to enable it to make your trace routes in your network working. So basically that's it at the moment. We started 3 minutes late, and I finished 3 minutes late, so I think that it's legitimate. And if you have any questions or any ideas or any comments, please share with me now. We have the question section, or you can use my email address there and drop me a message anytime, and I will of course respond. That's it. If you have something to say, please don't hesitate. Okay, I suppose that everything was so clear, so understandable, so so simple that you have no questions. Then that's it. Thank you so much. It was a workshop. And soon we will start our conference. See you on the opening. Thank you.